Okay, so let's take a look at more parameter estimation. So the question of parameter estimation was originally finding the population mean based on the sample mean. Mu is the population mean, x bar is the sample mean, and we'd like to find the confidence interval with a certain confidence level that will estimate the population mean. So we did this before. If n was greater than 30, we used the Gaussian distribution table and this equation here. So what do you do if n is less than 30? The table is called the student's t table, and it's used for several things, but we're using it mainly in this application of finding the mean. So when n is less than 30, we can't assume that the population standard deviation is about the same as the sample standard deviation anymore. But the equation using the student's t is a very similar equation to the one using the normal distribution. We use a different table. But we start with the same setup. We have a sample, we take a sample of measurements, n measurements. We find the mean, x bar. We find the standard deviation, s. And then we find, from table 6.6, we find the student's t for the given n and the desired confidence level that we want, like 95% confidence or whatever it is. And then we use this equation. So this is our delta here. It's t instead of z. It's s instead of sigma. It's still the square root of n. So n greater than 30 or n less than 30 looks very similar with just slightly different parameters here. So let's look at this table. Here's table 6.6. It's the student's t table. It's a function of alpha, which is 1 minus the confidence level, and it's a function of v, which is related to the degrees of freedom of a system. But in this class, v is always going to be n minus 1. So go ahead and mark up your book. Just cross that off or write n minus 1 right next to v, so you remember what that means. Then we have confidence levels here, and they're given by alpha over 2. So alpha is 1 minus the confidence level. Alpha over 2 is that thing divided by 2. And so if we know the confidence level, we can find alpha over 2, and that's which column we're using here. So again, these are basically the confidence levels, but in kind of a weird way to write it out. So if you're marking up your book, you might as well add the confidence levels here. So this is 80% confidence level. Alpha would be 0.2. Alpha over 2 would be 0.1. 90% confidence level, 95, 98, and 99%. So we can't do this for any arbitrary confidence level. We have the table just for these particular ones, but they're the most common. And I suppose you could interpolate if you needed to, or you could find a fancier table. The last useful thing to know is that down here we've got an infinity. This is n minus 1, the v, and so when v goes to infinity, it goes back to the Gaussian, the normal distribution. So remember in the last example we found that z alpha over 2 was 1.96 for 95% confidence, and so this would give it to us in a quicker way. If the confidence level and the Gaussian is one of these values, then just use this bottom row and save yourself a little bit of time. If you need 96% confidence level, then you can find that in the table, the other table. So save a copy of the student's t with n minus 1 instead of v and the actual confidence levels, and you'll save yourself a little time. So here's an example similar to what we've done before. We're measuring now 5 widgets instead of 35 was the last example, but we have the same average, 3.9, same sample standard deviation of 0.07, and we want to find the confidence interval of the mean, the confidence level of 95%. So again, these are the things we're given: the sample size, sample mean, sample standard deviation. So we find t from the student's t-table. So for n equals 5, we took 5 measurements. We have a v of 4, so we're in this row. And for 95% confidence level, our alpha over 2 is 0.025, so we can find the student's t-value right there, 2.776. Then we just plug it in to the numbers we're given with the student's t, and we find 3.9 plus or minus 2.776 times 0.07 divided by the square root of 5, and we get this number here, 0.087, as our delta with 95% confidence. So with 5 widgets measured, we're going to be less confident or giving a bigger delta here. So if you remember when we took 35 measurements, we have a smaller confidence interval for the same confidence level. Okay, so the last parameter estimation that we do in this chapter is the confidence of the variance. So again, not the confidence of the mean. That's the most common mistake people use, is a different equation. The variance, remember, is the standard deviation squared, population standard deviation. So we're trying to find the population standard deviation from a sample standard deviation. This uses a different table. So everything's table driven in this chapter. And this table is called the chi-squared distribution. And it's not symmetric. It has this shape here, and this is the area of the tails in the chi-squared table. So the process is very similar. We take a sample of size n. We find the sample variance, which is the standard deviation squared. And given the confidence level, we can find these chi-squared values from the table. So the range of values of variance, the low end is this one, n minus 1 times s squared divided by chi-squared v alpha over 2. And the upper bound has the same numerator, but the chi-squared v 1 minus alpha over 2 level. So these are all from the table. This equation is showing the confidence interval on the variance, and finding these chi-squared values, they come from this table. So remember, again, we have v in the table, so that's n minus 1. That's the table. The table here is chi-squared, not chi, so don't square it, just put that number in the denominator here. It's already squared in the table. And then alpha divided by 2 and 1 minus alpha over 2. Remember, alpha is 1 minus the confidence level. So if you have 90% confidence, alpha is 0.1, alpha over 2, 0.05. So this is 0.05, that's the 90%. 1 minus alpha over 2 is going to be 0.95 right there. And so these are all of the confidence levels written in a strange way. So we can rewrite them all like that. So if you're 90%, you use this column and that column to find the two chi-squared values. If you can't remember which one is which, this number has to be the less than. This is the smaller one, so we put the bigger number in the denominator here. So the inequality works. The smaller number goes over here. So you can mark up your table in the book to make it easier to use. Okay, so a quick example, just plugging in the numbers. We took a sample with n measurements. We found the sample variance was 16. We want a confidence level of 95%. So we're supposed to find the confidence in the variance. So that is straightforward application here for v of 14, because n is 15. We get the chi-squared shown in the table for 95% confidence. It's the 95% confidence and the 95% confidence value. N equals 15, v equals 14. So we plug those in and we find this range. So this is the confidence of the variance. We don't get a nice symmetric plus or minus. We get a lower bound and an upper bound for this calculation. If we want to find the largest possible standard deviation with a confidence level of 95%, it's here in the same answer. If we take the square root of both sides, 6.31 is the square root of this 39, and that would be the highest standard deviation with 95% confidence. Okay, so just a summary of the equations we've looked at for this parameter estimation topic. The confidence in the mean from the mean of samples can be estimated with this equation if n is greater than 30, with the student's t for n less than or equal to 30, and the confidence of the variance comes from the chi-squared table. Variance is standard deviation squared. So that's the 3 parameter estimations we're going to do. And I hope you can do the homework and take the quiz, and I'll see you in the next video.